Hello, grade 11s. Welcome to today's lesson on Charles's Law. Now, Jacques-Alexandre Senior Charles has a really long name. I'm sure that by the time his mom was finished yelling at him, which was the only time I ever heard my full name as a kid, he probably was long gone. It might have been the reason that he eventually became an aeronaut. He might have had time to get far enough away to go up in a hot air balloon. You see, back in the 1800s, astronauts were the big thing. Obviously, we didn't have space travel then, but aeronauts, hot air ballooning was. I can imagine a situation where Charles one day was sitting by a fire and had scrumpled up a piece of paper and thrown it onto the flames. Perhaps you've done something like this at one point, sitting beside a campfire, scrumpling up a piece of paper and throwing it over the fire. You may have noticed that sometimes, if the paper kind of had taken on a cup shape, it floated up on the hot air of the flames. Well, in Charles's case, he used this to come up with a relationship between volume and temperature. And what he said was that the volume of a fixed amount of gas is directly proportional to its temperature. Now, the temperature is going to have to be in kelvins here, but basically he said, if I raise the temperature of a gas, it will take up more space. So basically what we can say here is that if the volume increases, if my volume goes up, if it increases, the temperature will go up. Or the converse is true. If I make something hotter, the volume will go up. The same thing is true. When the volume of a gas goes down, its temperature goes down. And also the reverse. If I cool a gas off, it takes up less space. So the big deal is why. And any time that I ask you guys a question about why in chemistry, what I want you to do is talk to me about what are the particles doing. It always comes down to the particles and how they are moving and how they are changing. Now, when I apply heat to a particle, the particles will move faster. They'll bang around each other more and hit each other harder, and that, of course, will allow them to spread out. As the particles spread out, the volume or the amount of space that they take up is greater. Now, the best place we could think about this and when this might have happened in our own lives is thinking about birthday parties. And I noticed that there's two very different kinds of traumas around balloons at birthday parties, depending on whether or not you have a summertime birthday when it's hot outside, or, like me, a wintertime birthday when it is minus stupid outside. Now, for those of you who were born in July and August, you probably would have experienced your birthday party trauma in the summertime when you were little kids. When you're a little kid and you get to have an outside birthday party, quite often you probably asked for tons of balloons to be blown up to the size that they were ginormous, as big as they could get. And that was probably done all morning long while it was relatively cool outside. By the afternoon, at about 2 or 3, when all the kids were there, however, and those balloons started to heat up, the gas particles started to try to spread out inside the balloon. But if the balloon was already as big as it was able to stretch, it inevitably popped, which when you were little probably resulted in a lot of tears and crying. Now, for those of you who are born in the wintertime, in February and early March, when it is really cold outside, you'll notice a very different kind of trauma with balloons. When I was about 17, I didn't want to have a birthday party at my house anymore, which kind of stands to reason. You guys are about that age now. So my parents would say, how about we take you out for supper? Great, that sounded fantastic. They thought it was very funny to take me out for supper someplace where they'd put a tinfoil hat on my head and have all the waiters and waitresses sing me happy birthday and then hand me one of those helium balloons to walk with the walk of shame out of the restaurant. Back at that time, I probably, quote unquote, forgot my helium balloon in the car. I'm born in February, guys. In February on the prairies, it is definitely minus stupid outside. We're talking minus 40 on any given day. So that balloon, when it started off at plus 20 degrees Celsius or 293 kelvins, would cool off to minus 40 degrees Celsius. So if we have minus 40 degrees Celsius, we'll take 273 and minus 40 degrees Celsius. The temperature has dropped a ton. We're down to 233 kelvins. So what would happen to the balloon? Well, the balloon's gases would not move as fast. They'd get closer together, and the balloon would look in the morning kind of shriveled up and limp and like it had run out of air. However, if you bring it back inside the house and it heats back up again, the balloon will poof right back up again. Now, if you're looking for a weird little laugh to make your parents wonder about your teacher's sanity, go ahead and take 3 balloons. Blow them up to the same size. Put one of them somewhere in the middle of your house where the sun won't hit it. Put another one in some warm, sunny window where it will start to warm up, and go put another one in the freezer. That ought to cause some comments when your parents go looking for meat for dinner tonight. After about an hour, take a look and compare the size of the balloons to your one that had been held in the middle of the house, your control. And you'll notice that the temperature has caused a difference in the volume of the balloon. Now, the same thing happens in hot air ballooning. A fire or a little furnace at the bottom of the balloon here causes the particles of air in the balloon to spread out. They take up more space. Because the particles are so spread out inside this hot air balloon, the density inside the balloon is much less than the density of the cool air surrounding the balloon. Therefore, the balloon will float. So here's the formula for Charles's law. In Boyle's law, we had an inverse relationship. As one variable went up, the other went down, and we multiplied. In Charles's law, we have a direct relationship. As one thing goes up, the other goes up. And for a direct relationship, we divide. V1 divided by T1 is equal to V2 divided by T2. Now, it's really important here as we're doing these calculations, you guys, that we keep temperature in kelvins. As soon as you see a temperature in Celsius, I want you to cross it out and immediately change it to kelvins. Otherwise, you'll probably accidentally use Celsius and none of your math will work. Remember, Celsius is based on the boiling and freezing point of water, and let's be honest, most gases are not water. So here's our first example. And just like we did in the last unit, or with any problem solving in all of chemistry, as soon as I see a problem, I like to pick up a highlighter or my pen and circle and find all the numbers and their units. That is the first point, because that's what I'm going to be doing the math with. Then I'm going to pick up my pen and I'm going to read, and I'm going to use my readings to try to help me label which each of these things might be. Now, liters is a measure of volume. So this is the first volume I'm seeing. I'm going to call this V1. 4.4 liters of a gas is collected at 50 degrees Celsius. Degrees Celsius is a temperature. The word at links it to V1. They happen in the same instance. I'm going to label this guy T1. What will its volume be upon cooling it to 25 degrees Celsius? Again, degrees Celsius is another unit of temperature, so I'm going to label this T2, and they're asking me to find volume. So I need to pick a formula that has volumes and temperatures. All right, now before I go and try to continue here, I know I'm going to be picking the formula V1 over T1 equals V2 over T2, but my temperatures are in degrees Celsius, and that won't work in this formula. So I'm immediately going to cross these numbers out so I don't accidentally use them, and I'm going to add 273 to them to change them to kelvins. 50 plus 273 is 323 kelvins. This is the version of T1 that I'm going to use. 25 plus 273 is 298 kelvins, and this is the version of T2 that I'm going to use. Okay, let's substitute. In place of V1 up top here, I'll put my 4.4 liters. I labeled it up there. T1 was 323 kelvins. I'm putting that in the denominator spot. I'm just substituting here, folks. V2 was what we're looking for, so we'll leave that as a variable. And T2 is 298 kelvins. Now remember, this is a direct relationship. What happens to one variable should happen to the other. I can see my temperature's gone down a little bit. I'm going to expect my volume to go down a little bit. So how do I solve these kinds of problems? How do I solve this type of equivalency mathematically? Okay, well, the way we go about this is something called cross, multiply, and divide. I think that Mr. Bolton talks about something called super Z or something like that. Basically, we're going to look for an X. So I'm just going to take a highlighter here, and through the equal sign, I'm going to make an X. there's this line, and just to help you guys see, I'm going to make the other one in green. There's this line. You'll notice that one of my lines has two variables. The other one has the unknown. Okay? The one that has all the numbers, multiply those numbers together. So what we're going to do is we're going to go 4.4 liters. I'm going to times that by, multiply on the diagonal, 298 kelvins. So we're going to multiply that by, excuse me there as I try to write with a pen and a mouse. Doesn't always work the best for me here. 298 kelvins. Okay, cross multiply on the diagonal, and we're going to divide by the remaining variable. So I'm going to divide by this guy. So I'm going to divide it by 323 kelvins, 323, and that's kelvins. So what you're going to notice here is that your kelvins are going to cancel, and your answer is going to come out in the only unit we have left, which is going to be liters. So 4.4 times 298 divided by 323 on your calculator gives you 4.06. And just like we predicted, my volume decreased by just a little bit. Okay, let's try one more. Again, let's go looking for numbers and highlight them with their units. That's really helpful for us to understand what's going on. And then as we read, we'll be able to label them. Now, again, liters is a measure of volume. So I've got 5.00 liters of a gas. That's my volume. It's collected at, there's my linking term, 100 kelvins. How nice was I here? I'm not even asking you to do a temperature conversion. It's already in kelvins. It's then allowed to expand to 20 liters. Again, liters is a measure of volume. That's V2. What's the new temperature? There's my question. All right. For a mark on a test, write the formula down. You guys, this formula with the letters in it lets me know that you understand what kind of a question it is. V1 over T1 equals V2 over T2. Even though I let you have those formulas on your cheat sheet, it just shows me you understand what you have to do. Next step is substitute. We have 5 liters is V1 and 100 kelvins is T1. Remember, it's already in kelvins, so I can use it in this form. 20 liters is V2, solve for T2. Well, again, how do I do this? Well, just like the last question, find the two diagonals. Kind of look for that X that exists through the equal sign. One of them has two numbers in it. Take those two numbers and multiply them together, and then divide by the remaining number. Okay, so this is how that would look. It'd be 20 liters times 100 kelvins divided by the 5 liters. That's going to give me my T2. Again, we could predict the answer before we even did the math. My volume went up by 4 times. I'd expect my temperature to go up by 4 times. And when we do the math, indeed it does. Okay, guys, your textbook has a couple of trial problems that you can do on page 446 and some more explanation about Charles on page 444 and 445. What I'm hoping you've learned in this video is that, can you explain the relationship between temperature and volume in terms of how the particles are moving? Can you tell me why I have to have temperature in kelvins in order for Charles's law to work? And can you use the Charles law formula to calculate problems involving temperature and volume? You have 2 worksheets in your workbook on pages 14 and 15 for you to practice. This will be the second last lesson for this week. Tomorrow's lesson will be on Gay-Lussac's law, and that will be it for the spring break. If you have any questions, shoot me a message in Teams or post below this video.